All right, let's take a look at section 6.4 in your text, water vapor and air. Almost all air contains some water vapor. Absolutely dry air, that is, air without water vapor, is rare. Like air, water vapor is a gas. Consequently, it exerts pressure on the surfaces of the enclosure containing it. However, although air and water vapor are thoroughly mixed together, the pressure exerted by the water vapor is independent of that exerted by the air. In other words, air pressure and vapor pressure act separately on enclosure surfaces. The diffusion of air and the diffusion of vapor through a building envelope are independent of each other and are controlled by their own individual pressure differences across the envelope. In other words, the diffusion of air is related to the air pressure difference across the envelope, and the diffusion of vapor is similarly related to the vapor pressure difference. Like air, vapor has two means of migrating through a building assembly. The first is vapor leakage through holes, gaps, cracks in the assembly. And the next is vapor diffusion through the body of the assembly, through the walls, the solids, and building components like such. It is important to note that, like air, vapor flows from the warm side to the cold side of the envelope. Thus, in cold climates, vapor tends to flow from inside to the outside, and in warm, humid climates, vapor tends to flow from the outside to the inside. In other words, heat flow and vapor flow are generally in the same direction. In the next part of Chapter 6, let's take a look at the condensation of water vapor. The temperature at which the air's relative humidity becomes 100%, and that's when the air is completely saturated, is called its dew point temperature, or simply the dew point of air. If the temperature of the air is decreased below the dew point, the water vapor in air converts to a liquid, a phenomenon known as condensation. The condensation of vapor inside an envelope assembly is referred to as concealed condensation, as opposed to surface condensation, which occurs on the envelope surface, such as a window glass. Since both concealed condensation and surface condensation are undesirable, our goal would be to eliminate each of those, or condensation altogether. One way to eliminate surface condensation is to simply increase the R value of the assembly. The effect of R value of an assembly on the location of the dew point during a heating season. So if I have a warm interior and a cold exterior and a low R value, or maybe no R value at all, I'm going to end up with surface condensation. When we increase the R value, same situation, warm interior, cold exterior, and an assembly with a higher R value, I'm going to end up with condensation that falls somewhere, or a dew point that falls somewhere inside of that assembly. And that's where my condensation is going to occur. So these are both issues that we want to eliminate in our building design. In order to eliminate concealed condensation and surface condensation, we have to look at ways or materials that can be used as vapor retarders. Take a look at Table 6.1 in your text on page 156. Table 6.1 gives us a list of commonly used building materials that are found in most building assemblies. What we're interested in here is the perm rating of these different types of materials. So for most vapor barriers in this area, we typically use 6 mil thick sheet of polyethylene. The vapor or the perm rating on that is 0.06. If we step that up, make it a little bit thicker, and we go to an 8 mil thick sheet, our perm rating doubles. It goes to 0.03. The lower the number, the better the ability of the material to resist vapor, or to keep the vapor from passing through it. So if we go up to 15-pound asphalt felt, the perm rating on that is 4.0. Brick masonry is the same, it's 4.0. Those are really not very good in terms of not allowing vapor to pass through them. Unpainted gypsum board, vapor can pass right through that. Building paper grade B is 1.0, and just some of the other ones. Paint's actually a fairly decent vapor retarder, according to this chart. So how do we select an appropriate vapor barrier? The International Building Code gives us prescriptions for the use of vapor retarders. If you take a look at page 157, a selection of appropriate vapor retarder materials, there's different climate zones. In fact, we're in climate zone number 4. So we would, let's see here, it says class 1 vapor retarder is not to be used on the interior side of wood frame or cold form steel exterior walls. So we cannot use them on exterior walls, but we'd want to use them on interior walls. So a class 1 has a perm rating of 0.1 perms. Class 2 is 0.1 to 1 perm, and class 3 is 1 to 10 perms. So let's take a look at the location of vapor retarders in the assembly. Per the building codes, a vapor retarder, either a class 1 or class 2, is required on all interior surfaces of the envelope in climate zones 5, 6, 7, 8, and in marine 4. The objective is to prevent interior vapor from migrating into the envelope assembly where it could condense. Because a vapor retarder encloses an interior space completely, as shown, interior vapor will not permeate into the envelope assembly. However, to ensure any unintended small amount of interior vapor which may migrate into the envelope assembly does not condense there, an assembly beyond the vapor retarder should be vapor permeable. So if by chance vapor does penetrate the vapor barrier, that exterior assembly should be able to breathe. That water would then migrate to the air retarder and it would diffuse through it. That's why the air retarder is not completely 100% watertight. It has to be breathable. Let's take a look at the importance of attic ventilation. Ventilating the attic is necessary for reasons other than condensation control. In cold climates, ventilation prevents the formation of ice dams at projecting roof eaves. If the attic is not ventilated, it remains relatively warm because of entry of heat into the attic from the warm interior, but the eave overhangs are cold. This melts the snow in the middle of the roof, which freezes again at the eaves, forming ice dams. The problem is worse in a roof ceiling assembly with inadequate insulation. Soffit ventilation is considered as intake ventilation. Adequate ventilation of the attic requires cross ventilation, requiring intake as well as exhaust ventilation. Because warm air rises, exhaust ventilation is required at a higher level in the attic. There are 4 different alternatives used for exhaust ventilation: gable ventilators, ridge ventilators, and turbine ventilators. Gable fans can also be used. There are 2 main options for attic ventilation. One would be the use of gable vents, and the other would be the use of ridge vents. In both cases, air is entered through the soffit vents and it exits through the vents at the roof. Here's an example of turbine vents and gable fan vents. Take a look at principles in practice beginning on page 160 in your text.